We talked about conservation equations for mass, momentum, energy, and entropy. So let me write down the equations as a quick review. So we have the difference between controlled mass and the controlled volume. And let's start with mass. So that's the m equals 0. For control volume, that's mass minus mass in plus mass out. That's the rate of change equals 0. And for momentum, we have rate of production equals the rate of change. And then for controlled volume, we have minus m in dot v in plus m out dot v out plus dp dt equals sigma f. And we have conservation of energy, which is our first law. Basically says q dot plus w dot. We define the outflow as positive plus the rate of change in the system equals 0 for control volume. Or we can have the time integrated form, which is q plus w plus delta e equals 0. For control volume, we can have mass flux, so there's one additional term. Where HI is the total entropy associated with ice flow. Now let's finally look at entropy. So entropy flux plus the change of entropy equals to entropy generation, which is non-negative, or time integrated form. For control volume, we also have mass flux, so that's so those are all the basic equations about conservation laws. So let's move on to the second section. So in this video, we'll be talking about entropy and exergy, which is related to entropy, and also we're going to talk a little bit about efficiency. So let's start with entropy. So like energy, entropy is also an extensive property. It basically measures the disorder of the system. And as second law tells us, entropy should always go up, which means that we lose the ability to do work. So so now let's move to the path to see a few examples of entropy. Hopefully you can get a better understanding of why entropy generation means loss of the ability to do useful work. So let's start with the cycle of a simple compressible substance, which means that there's only two parameters to describe the system. And for this, we choose S and T. So we have a cycle. A cycle basically means that after we start with some initial state, and as we go through a series of processes, it will end up with exactly the same. So apply second law. Suppose we make a small change, and there's a heat flux associated with that change. So second law tells us that ds equals to entropy generation at that step, which is larger than 0. So if we rearrange this, we'll get ds equals to minus del q over t plus d sigma. And we can do a path integral. Since the cycle basically recovers in initial state, we'll get the path integral of this part as 0. So we'll get this. And since this term is always non-negative, we'll get the Clausius inequality just from second law analysis. And notice that for a reversible process, which we don't have any entropy production, so we can achieve equality. Otherwise, this should always be. Let's look at another example of entropy generation in heat conduction. So suppose we have two different heat sources, high temperature source at temperature T and a low temperature source at temperature TB. And if we draw a control volume like this, you'll see there's gonna be heat flow into the system from the high temperature source, and also heat flow out of the system. And we can assume that within the control volume is steady state. Basically means the total internal energy doesn't change. So if we apply first law, we get Q in dot plus minus Q in dot plus Q out dot plus dE dt equals 0, and this term is 0. And we're gonna, if we apply second law, we'll get okay, so we combine these two, we will get, and this is also 0, we'll get the entropy production rate within the control volume. That is and since TA is larger than TB and this term is always non-negative, the entropy generation is always positive for a heat conduction problem with finite temperature. Take a look at a more general case. Suppose we have a general control volume like this. We're going to look at the entropy generation due to heat transfer across the control volume boundary. So that will be and we're gonna apply Green's law, which converts a surface integral into a volume integral. And we're gonna say that this part, and we can see that this part is the reversible entropy generation due to heat transfer. Because if we have say a uniform temperature, this term is basically 0. And as for this part, if we further apply Fourier's law, we get Q equals C minus K gradient of T, and this will actually become and it is always non-negative, so that's the irreversible entropy generation due to heat transfer. And basically this part basically tells us that the only way to transfer heat without creating entropy is to have infinitely small gradient temperature gradient. That was entropy. Now let's take a look at Exergy. So we know that first law tells us energy is always conserved, but sometimes we are not interested in energy itself because it does not tell us how much work we can get from the system. So let's take a look at an example of a control mass. And suppose it has some interaction with the environment at T0, and there's going to be a heat transfer of Q0, and also it's in contact with some high temperature sources Qi at temperature Ti, and we're going to extract some work from the system. We want to get an idea, get an equation for the amount of work we can get out of the system as a function of these variables. So if we apply first law, we get and second law tells us and then if I combine these to try to eliminate Q0 term, we'll get an expression for W, and that is now let's take a further look. We can group them into three parts. The first part is basically supply from the high temperature sources, so that's the supply to the system. And the second part has nothing to do with QI itself. It's just a function of the initial and final state of the system as well as the environmental constraint. And the third term is always non-positive, and that's basically the destruction of ability to do work due to entropy generation, and we call this term irreversibility. So that's this term, and it's always positive. So now let's, for the sake of discussion, now let's assume this term is 0, so there's no heat transfer into the system. And we'll take a look at if we have a system like this, the maximum amount of work that we can extract happens when the irreversibility equals to 0. So basically that's an reversible process. So work max equals to work reversible, and that happens when this term is 0. So that's minus ECM plus T0 delta SCM. And if you write them in terms of initial and final state, suppose it goes from state 1 to state 2, and that's going to be E1 minus E2 plus T0 S1 minus S2. So it's a function of the initial and final state. And let's take a look at a special case where the final state is the environmental state, and in that case we'll have E2 equals to E0, which is internal energy of the system when it's brought to equilibrium with the environment, and also T0 S1 minus S0. So basically that's the amount of work maximum amount of work we can extract from the system when there's no heat transfer and when we bring the system to the environmental conditions during reversible process. Note that this is not the final answer we want to get. What we want to get is the maximum amount of usable work. That's different from the maximum amount of work from the system. So what are we missing here? We're missing the expansion work down to the environment. So basically, this control mass is going to expand, and that will do some work to the environment because there's pressure outside. So we have to subtract that amount of work. and so the amount of useful work. Useful, and from state 1 to 0 equals to the equation above sorry, this should be minus, and plus the an additional term that's due to expansion work. So basically, this is a useful work that we can extract from the system at initial state 1. So we can we can define this quantity as we call it the exergy of a controlled mass, and we denote that as phi. And also we can express that in mass-specific form, which is m times little phi. So that's exergy for control mass, and that measures the ability to do useful work. So now let's take a look at the control volume. So the difference between for control volume is that there can also be mass transfer. So we can have mass inflow, and there will be total entropy flux associated with that, and outflow, and we're gonna extract some work. So first law takes the form of now we have this additional term plus a change plus work equals to 0. And second law, and we also have a conservation of mass. And we can assume it's a steady state process, and that basically applies to most of the applications we can encounter in real world. And steady state tells us that this time derivative basically 0. So this tells us that inflow and outflow basically equals to each other, and we can define them as m dot. So now if we go back to these two equations and try to cancel out this term, we'll get similar equations as we did in control mass, but we have a additional term due to the mass transfer. So let me write it down, and it should be W equals to sigma qi. And minus the disruption due to entropy generation. Oh, we're gonna express everything in rate form. So I was missing the dot here. So again, this term is supply of exergy due to heat transfer, and this term is basically the exergy flux, and this term is destruction or irreversibility due to entropy generation. To sum up, for controlled mass, we have exergy equals to the amount of work, useful work, we can get from state 1 to state 0, and that's E1 minus E0 plus T0 minus, and for control volume, and we denote that as m dot phi, and that equals to so basically Exergy is measure of the ability to do work, and that's the maximum amount of useful work we can extract from the system from a certain initial state, and during the process of bringing it to environmental state. And we know that is the function of the system itself, the initial state of the system itself, and also the environmental variables T0. So Exergy basically takes the unit of energy, but it's different from energy because it's not a conserved property. It's always decreasing due to destruction, due to energy generation, entropy generation. So the actual amount of work we can get is always going to be the from 1 to 2 useful work. Is always going to be the Exergy difference from 1 to 2 minus the destruction term due to irreversibility, and this term is always non-negative. So the actual amount of work is always less or equal to the reversible, the amount of work we can get during reversible process. And this is typical, is always T0 times entropy generation. This is Exergy. Now let's talk about efficiency. Basically, efficiency is a measure of the performance of a thermodynamic system in fulfilling some tasks. It's always defined as what we get out of the system over what we put in, and depending on which measurement we choose, we can have first law and second law efficiencies. So basically, first law efficiency is the energy we put in over energy we get out over energy we put in, and second law efficiency is defined based on Exergy. Now let's take a look at a few examples of first law efficiency. With nozzle. So nozzle is a device that converts internal energy to kinetic energy. And we define the efficiency of a nozzle as the amount of change in actual amount of change in kinetic energy over the amount of change in kinetic energy during an isentropic process. So that means and it's always less or equal to 1. Now let's move on to a turbine. Basically, a turbine converts the internal energy to work. So a turbine efficiency is the actual amount of work output over the amount of output during an isentropic process. So that is H1 minus A2, H1 minus H2 isentropic, and also is less or equal than 1. And we can also have a compressor. It's just a reverse process of a turbine. So for a compressor, we put in some work to the system to raise the internal energy or entropy of the system. So that is defined as the amount of work input during an isentropic process over the amount of input during an actual process. So that is H2 isentropic minus H1, H2 minus H1, and that's also less or equal than 0. And we can also have heat engine, heat pump. So we can have some high temperature source and low temperature source. We're gonna have an heat pump here. We're gonna dump in some. We're gonna supply some work, and that will basically pump some energy from the low temperature source to the high temperature source. And the coefficient of performance for heat pump is defined as the amount of energy transferred to the high temperature source, because that's we want it over the amount of work we put into the system. So that is also equal to the amount of heat transfer from the low temperature source plus the amount of work divided by the amount of work. And this number is always larger or equal than 1, but it's limited by the best number, which is the coefficient of performance of ideal cycle, which is the reversible. For second law efficiency, basically the measurement changed to Exergy. So for our work producing device, the second law efficiency is defined as the actual amount of work we can get from the system over the maximum amount of work, or the amount of work we can get from a reversible process. And for work consuming device, second law efficiency is defined as the supply of work during a reversible process over the supply of work during the actual process. And for heat pumps or refrigerators, the second law efficiency is defined as the coefficient of performance divided by the coefficient of performance over a reversible process. So for second law efficiency, it's always less or equal than 1. This is the end of this video. Next time we'll take a look at several cycles, and we're gonna apply Exergy analysis, and we're gonna compute the efficiency, first law and second law,